Okay, now it's working.
Okay, thank you. All right. Hello, everyone. Thank you for being here for the next iteration of Rocky World's discussion series. Today, our speaker will be Professor Emeline Bolmont from the University of Geneva on tides in rocky worlds, impact on habitability. And like at the previous iterations, so what we will have is a 30 to 40-minute talk by Professor Bolmont. Then we will have a plenum discussion with Q&A and also go into hopefully some more interesting discussion over time. And then we will close before the end of the hour. Regarding the netiquette, please, when you use your full name while you are in this meeting so that we can identify you with a real name or publication name. Please keep muted throughout the talk. And when you ask a question or give a comment later on, please raise the hand via the Zoom hand raising option. And when you speak out of respect to the other people in the room, please, if at all possible, display your video when giving a comment or asking a question. And with this, I will actually give over to Emeline. Please, Emeline, we look forward to your talk.
Yeah, thank you, Tim. Can you see my screen and now the slides?
Yes, everything works. Thank you.
All right. Well, thank you very much for giving me the opportunity to talk to you today. So yeah, I will be talking about tides in rocky worlds and about the impact on habitability, but not only, let's say. So what I'm going to show you is work that was done in our group in Geneva. So you have a list of a lot of names that are more or less connected to what I'm going to show you today. And just this work was also done in the framework of the Life in the Universe Center that was created in Geneva 2 years ago now. And so this center, the aim of this center is to perform interdisciplinary science between all these different disciplines that you can see now on the screen. And so, yeah, the work that I'm going to show you is also, in this framework. And the idea of this center, as I think, which is an idea or a goal shared by a lot of people, I guess, is to understand the origins of life on Earth, but also try to determine if maybe we might not be alone in our universe. So, the big question is there life out there? As you know, this question, which is a very long-term goal, I guess, of exoplanet science, is a very complex question, and also it relies on a lot of hypotheses that we do about life. And in particular, here we are talking about life as we know it, so life that requires liquid water, like you can see displayed on this image, for instance. And this life also has to be sufficiently evolved to have impacted the chemical composition of its atmosphere. Because in the end, when you work on exoplanets, the ultimate goal is to look at the atmospheres of this planet and detect potential signs of life. And in order for signs of life to be detectable in the atmosphere, then you need, a flourishing life that can impact significantly its atmosphere. And the atmospheres are the only, let's say, manner to probe the potential for life for the exoplanets. Of course, it's not the same idea for the solar system where you can actually get there. But so that's the ultimate goal, let's say. More personally, what I'm interested about is how do planets get habitable? So how do we go, from a protoplanet which probably has a magma ocean at its surface, then probably degasses some atmosphere, it cools down, and eventually, if the conditions are right, you can have, water condensation and some habitable planets, habitable in an astronomical sense, so with just the presence of liquid water at the surface. So that's a question that is driving a lot of what I'm doing. And also a kind of a backup question, so I'm more of a modeler, but a backup question, of course, in the back of my mind is also, okay, what kind of signatures of life could we hope one day to detect, for these planets that we are observing. So the planets that are interesting, let's say, at the moment in the search for life or for these kind of questions are not planets like our own Earth around the Sun-like star. We have not yet detected such a planet. But we have been detecting a lot of planets around much lower mass stars, and in particular cool dwarfs or ultra cool dwarfs like the TRAPPIST-1 star or Proxima Centauri. And these stars are much less luminous than our sun, so the habitable zone is closer in. Usually the systems are you have more than one planet in a system. Those are multi-planet systems with the planets so close into the star, often in compact systems, etc. So those planets are being observed today. We have a few of them that are in a habitable zone around these low mass stars. But what makes them maybe particularly interesting is that these habitable zone planets are the only habitable zone planets available for atmospheric characterization nowadays and in the near future. So as you know, James Webb has been observing the TRAPPIST-1 system. I think that by now all of the planets of the TRAPPIST-1 system have been probed by James Webb, more or less. And also in the near future, we will have access to instruments like RISTRETTO at the VLT or Andes at the ELT that will also do atmospheric characterization for non-transiting planets like Proxima-b and try to estimate their atmospheric composition with the reflected light that we receive from these planets. So right now, all these techniques work for these planets around low mass stars. But we don't have yet, the instruments to do something with an Earth-like planet around a Sun-like star. So even if we were to detect one tomorrow of such planets, we would have to wait maybe 2050s with the arrival of life, for instance, the interferometer from space or HWO to characterize the atmosphere of such objects. So in the meantime, it's nice to focus on these guys, so the habitable zone planets around low mass stars. But these planets, these systems are very different from the solar system. I already gave a few reasons. The one I'm going to focus on is the proximity between the planet and the star, because these planets are very close to their own stars, and so they are going to be impacted by tides somehow. And so I just wanted to go through a few of the effects that are due to these tidal interactions. So first, let me differentiate between the stellar tide on the one hand. So the stellar tide is the deformation of the star due to the presence of the planet. And the planetary tide, and so the planetary tide is the opposite, is the deformation of the planet due to the presence of the star. So this planetary tide, so basically you deform the rocky part of the planet. It also impacts, the ocean if the planet has one, and you can also have tides in the atmosphere as represented in this light blue shape over here. And these two types of tides have an impact on the orbits of the planet. So it can drive migration of the planet outward or inward. It usually leads to a damping on the eccentricity of the orbit. The planetary tide impacts the rotation of the planet. So it tends for the rocky tide, it tends to synchronize the rotation of the planets and also decrease the obliquity of the planets. And also because, these planets are being deformed, you have friction inside, and so you create heat. And so you also have the planetary tide leads to a tidal heating inside the planets. And to illustrate that, I just put an image which I really like from Io, so the first satellite in the Jupiter system, which is the most, the most tidally heated body of our solar system. And so here in this infrared image, you can see the day side on the left over here, and the night side on the right. And you can see on the night side all these bright spots in infrared that correspond to hot spots through where the heat created by tides escape to space, basically, the planet, the satellites. And the thing that's all these quantities, so distance, rotation, heat flux, which are then, impacted, driven by tides, have an impact on the climate. So the distance and eccentricity impact the amount of energy that your planet receives. And for instance, if you have an eccentric orbit, you will receive more energy at periastron than at apoastron. So you can imagine freezing over at apoastron, for instance. For the rotation, it impacts the heat redistribution of your planet. So, the global circulation, the wind patterns. And if you have an obliquity, you'll have a seasonal effect. And the tidal heat flux, it adds like an additional source of energy. And it can also drive volcanism and in some cases, plate tectonics as well as was proposed by Zanadzi and Trio in 2019. And so if one day we want to maybe claim a detection of life around these planets, we really have to take into account, this whole complex picture, which can be even more complex if you add the fact that if you have additional planets in a system, they will impact the orbits, they will impact the rotation, and then also the tidal heat flux. So it's a very complex picture. And we really need to understand these systems as a whole. And I'm not even telling about, the impact of the star on the atmosphere. So just this part is already very complex. That's what I mean. And also, so for the tides themselves and also for the climates, the internal structure of the planet is very important. So the internal structure of the planet will tell you, for instance, the timescales of evolution, of the tidal evolution, so the timescale at which, for instance, rotation is going to evolve. And the internal structure is going also to have a strong impact on the atmosphere of the planet, because, for instance, through volcanism, you might, put in the atmosphere different species for different internal compositions. So the internal structure of the planet is paramount, for all these pictures that I'm showing here. So in this talk, I will tell you about rotation and tidal heat flux. And I will start with rotation. So in this talk, I will also focus on one system, because it's the perfect system for me. So it's the TRAPPIST-1 system. I guess you all know it. You have 7 planets around a very low mass star, about 10% the mass of the sun. So this star is very faint compared to the sun, so the habitable zone is located way closer in. And in this habitable zone, you have a classical habitable zone. You have 3 planets, E, F, and G. And you can see that this system is also a multi-planet system. You have more than 1 planet. And so if you want to, simulate the evolution of these planets, for the orbit, for the rotation, for everything that you want, you need to take into account the fact that you have more than 1 planet. And so what it means is that you need an n-body code. And so the work I'm going to show you has been done with Posidonius, which is an open source code, which you can find at this address down there. So the idea is to have a dynamical core, which is basically an n-body code. So in Posidonius, we have at least 2 n-body codes, so WH-fast and AS15, which are integrators for the orbits that were developed by Hanno Rhein and collaborators for the rebound for the rebound code. So we use these integrators, and we plug in different effects that we think might be relevant for some systems. So of course there is tides, but we also allow the user to add the effect of rotational flattening, of general relativity. You can also take into account the fact that the radius of a star, evolves with the age. And because radius is very important for tides, you might want also to take that into account. And also we have a very simple prescription for protoplanetary disk, which is just a fancy way of saying that we have a prescription for a type 2 kind of migration available also in the code. But here we want to talk about tides. So let me just tell you what are the tidal models that are implemented in this code. We have the constant time lag model, which is a simple kind of equilibrium tide model. So it's simple in a way that it's easily implemented. A lot of people are using it. But the caveat is that it only works for planets that are made of weakly viscous fluids. So typically it could work for a gas giant, for the equilibrium tide of a gas giant. But for instance, if you have a rocky planet, rock is not weakly viscous. And so that model should not technically be used for rocky planets. There is also an implementation of the creep tide model, but I'm not going to go into the details for this one. I wanted to highlight the last one, which is an implementation of the Kaola formalism for tides. So I'm not going to go into the details, but basically the strength of this formalism is to allow to consider any kind of planets that you want if you have the tidal response of these planets. And so it can work for gas planets, it can work for rocky planets, it can work for rocky planets with an ocean on top, with an atmosphere. But basically, anything you can think of, it can be then you can then compute the evolution of these planets. And so this model was implemented by Alexandre Revol, that you see in picture over here, and who is attending the seminar. So if you have questions about his work, you will be able to directly ask him if you want. But so Alexandre has been doing this huge work of implementing very complicated equations in Posidonius code to allow for to allow to compute the rotational and orbital evolution of real rocky planets, let's say. So rocky planets that have the response of like a realistic rocky planets. And of course, one of the first things that he did is to apply the model to TRAPPIST-1. And in particular, the question that we wanted to address was, what about the rotation of the TRAPPIST-1 planets? So you could say, but why do we care about that? We know the TRAPPIST-1 planets, they have to be tidally locked because they are very close to their star. Tidal locking is something that is very fast, and so that's it, But things are not as simple as that. So if the planet was alone in a system, then sure, no problem. So basically, as I was saying, the tides in the planet are like super efficient to align the bulges of the planet with the direction of the star, and in practice, this has the impact of locking the rotation of the planet, so that the spin of the planet is equal to the mean motion or the orbital frequency around the star. So that is true for one planet over around one star. But what happens if we add a planet to the picture? Here, what changes is that you have planet-planet interactions, so gravity between the two planets, and these planet-planet interactions are going to modify slightly the mean motion and also, of course, the eccentricity of the planets. So the tidal locking is that the spin is equal to the mean motion. But if you have another planet that modifies a bit your mean motion, it means that the spin of the planet has to constantly try to be equal to the mean motion that is varying with time. And so basically the spin is always trying, to become equal to the mean motion. And in some cases, the mean motion variations are such that the spin cannot keep up with it. And that's exactly what we observe for the TRAPPIST-1 system. So this is the result of a simulation done by Alexandre with Posidonius. So what you are looking at here is the spin ratio. So it's the spin over the mean motion. So at 1, it means that you have the tidal locking. So the real tidal locking, omega is equal to n. And all the colors here that you can see are this value of the spin over the mean motion for all the planets. And you can see that it's a bit all over the place. So it's not very far from the tidal locking, but it's not perfectly tidally locked. It's like oscillating around. So what does it mean in practice? One way to see it is to look at the position of the substellar point. So imagine that you're at time 0, you are sitting under on the substellar point. So meaning that the sun is directly above your head. What's going to happen is that you are going to your position compared to the star that should stay right above your head if you are purely tidally locked, the position of the sun is going to change a bit. And this is what this plot is showing you. So this is the substellar point position in degrees, and here you have the time. And you can see that for all the planets, you have an oscillation. So it would be like if you saw the star in the sky change position a bit like that. And it's not only oscillating, but you can see also a kind of a drift of the substellar point happening here over 1 year. So it's only for the sea planet, it's less than 10 degrees. So it's not a lot. But just visually, what does it represent? So imagine that you are sitting, so under the sun at time 0. It means that as time goes by, what you're going to experience is this. So for you, you will have the position of the sun oscillating, and little by little, the sun is going to slowly, move in the sky. And so if you wait long enough, you might actually do a complete turn of the planet, and so live like a day-night cycle, if you wish, but then a very long day-night cycle. So this is what is represented here on this graph. So here you still have the substellar point position, but here instead of 1 year, you have 60 years, and you have all the planets. And you can see, for instance, that for the planet C, in about 20 years, you go from the middle of the day side to the middle of the night side. And in about 40 years, you do a full rotation. So this, for instance, a bit less than 40 years for TRAPPIST-1c is what we call a sidereal day. So it's the duration of 1 day, a day-night cycle. So that in the end, for your planet, instead of being purely tidally locked, well, you're going to have a day-night cycle, but much, much longer than 1 day. And so what Alexandre found is that for TRAPPIST-1b, you have the duration of a sidereal day is more than 1,000 years. So basically, it means that TRAPPIST-1b is like essentially tidally locked. But for the other planets, the sidereal day is less than 100 years. And in particular, if we are thinking in terms of habitability, TRAPPIST-1e has a sidereal day of 81 years. So it means that if you are sitting at time 0 in a substellar point, 40 years after, you are in the middle of the night side. And so here we can wonder how this would impact actually the climate and the potential habitability of this planet. Because most of the studies that were looking at the climate of TRAPPIST-1e were assuming a perfect tidal locking. And so in this configuration, what happens is that you have a big ocean on the day side of the planet, and you are covered with ice on the night side of the planet. But imagine now that you start this way, but 40 years later, substellar point is on the other side. So it means that you probably melt this ice over here, refreeze water on the other side. So what would be the impact on the potential habitability of TRAPPIST-1e? Would it mean that the ocean is bigger? Maybe on the contrary, the ocean will be smaller, maybe disappear. So these are really open questions, but I think interesting. All right. So now let's move on to the tidal heat flux, and still then in the TRAPPIST-1 system. So here the idea was to say, okay, we know the TRAPPIST-1 system. We have pretty good precision on both the radii and masses. So this was a paper of Eric Agol in 2021, where you can see the planets on this mass radius diagram. So you see that indeed error bars are rather small, and the composition of the planets are maybe a bit lighter than the composition of the Earth. But as I'm sure you all know, having the mass and radius of a planet is not enough to constrain its internal structure. You still have a lot of degeneracies in terms of composition, for instance. And so that's the question that we wanted to address, because we don't know, maybe the planet, has no core, maybe it has a huge core, and, the composition between this planet and that planet is going to be very different. And so the question that we wanted to ask is how these uncertainties about the internal structure and composition of the TRAPPIST-1 planet impacts the tidal heating that we would compute for a given configuration of the planet. So to answer this question, we try to derive a variety of internal structure for all the planets of TRAPPIST-1. So here I show you for TRAPPIST-1c. So all these internal structures were computed by Mariana Villamil-Sastre during a master physics work in Geneva in our group, and she's now doing a PhD with team in Göttingen. And so during a master physics work, she computed different profiles with the Bolmont code for different composition and different sizes of cores, basically. And so here, all of these profiles, are for the same planet in terms of mass and radius. So we have the first case is a coreless planet. So yeah, no cores is the blue line. Then we have in orange the biggest core that could explain both the mass and radius. And so if you have a big core, it means that the core should be in should have a light composition to be able to reproduce the mass of the planet. And then we decrease here the size of the core. We have a Mercury-like case, an intermediate case, an Earth-like case, and a smallest core case, which then correspond to the heaviest core composition, because then you need the core to be much denser if you want to reproduce the same mass as that one, for instance. So with all these internal structure profiles, so we have density, we have viscosity, we have shear modulus, then you can compute the tidal heating inside the planet and as a function of the radius of the planet, so where you are in the planet. So here you have the center of the planet, here the surface, and here you have the volumetric tidal heating. So the black line is the coreless planet, and the colored lines are the ones with a core. So the first thing that you can see is that the tidal dissipation occurs in the mantle. So here, 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 and here. We don't have any dissipation in the core because we assume the core to be liquid with a zero viscosity, basically. So it was expected. Then you can see going from zero core to a big core that you increase the dissipation, so with the core size or the decreasing mantle size. And this was done for one assumption of the eccentricity of the TRAPPIST-1 planet allowed by the observation. And these other lines that I just make appear are for a different kind of assumption for the eccentricity of the planets. And so for TRAPPIST-1c, there is quite a big uncertainty about the eccentricity, which is then visible in the tidal heat flux. So the tidal heat flux is much bigger if you have a bigger eccentricity, obviously. So this is the heating profiles, but if you look at the total heating that is generated, so if you integrate that, basically, you get this for TRAPPIST-1c. So this is the tidal heat flux for different assumption of the surface temperature that were done in the internal structure models. And we compare this tidal heat flux with the one of Io, the red triangle. And for the Earth, we have here the heat flux of the Earth, which is tide, but mostly radioactive due to radioactive decay. And if you want to look at the tidal heating of Earth, then you are here, this triangle at the bottom of the plot. And so here, the blue area shows you the uncertainty that we have on the tidal heat flux of TRAPPIST-1c due to the uncertainty we have on the internal structure of the planet. Because here at the bottom, you have the circles and the triangles pointing up, which correspond to the smallest core and the coreless planets. And at the top here, you have the biggest core, which allows for the most tidal dissipation. So here, the extent of this blue area gives you the uncertainty that we have on the tidal heat flux due to the degeneracy of the internal structure. And this is for the minimum eccentricities allowed by the observation from Agol's paper in 2021. If you look at the highest eccentricities allowed by the observation, you have the green area. And you can see that the uncertainty that we have on the eccentricity is even bigger than the eccentricity that we have on the internal structure itself. And you can see it's more like maybe almost 2 orders of magnitude between the tidal heat flux of that guy, for instance, and that guy. And you can see also that there is a very little impact on the assumption that we make on the surface temperature of the planets. So now let's see what we have for all the planets. So here it's the same kind of plot, but instead of for one planet, you have B, C, D, etc. until H, still compared to Io and the Earth. And still the same color code. So the blue curves are for the lowest eccentricities allowed by the observation, and the green are the highest eccentricities allowed by the observations. So of course you see that the farther away the planets are, the less dissipation you have, which is logical because tides are much stronger if you are closer to the star. And you can see here the eccentricity uncertainty is bigger for the inner planets, and then for the outer planets, the eccentricities are better constrained by the observation, and so you have a better overlap between the blue and the green region. So basically, it means that for the outer planet of the TRAPPIST-1 system, the uncertainty we have on the tidal heat flux is mainly due to structure, to the internal structure, and here it's mainly due to the uncertainty of the eccentricities for the inner planets. But what we can see is that TRAPPIST-1b and C might dissipate way more heat than Io. The 2 outer planets dissipate way less than the heating flux of the Earth, and you have some guys in between like D, E, and F. And just in passing, so the TRAPPIST-1e, so it could have a tidal dissipation in this range. So it could potentially have a strong volcanism, and maybe also this activity could drive plate tectonics if we believe the work of Zanazzi and Trio that I mentioned earlier. One thing also I wanted to show you, so here is the tidal heat flux, so it's a flux. Maybe we can compare it to the top of the atmosphere flux. So here are the values from Elsa's paper in 2020, Ducrot et al. 2020. And you can see that for TRAPPIST-1b, actually, if you take the worst case scenario, So you consider that TRAPPIST-1b as the biggest core it can have, and it has the highest eccentricity allowed by the observation. You actually have a tidal heat flux equivalent to the top of the atmosphere flux, meaning that your atmosphere is heated as much from the top as from the bottom, which is kind of a cool situation to think about, let's say. The final thing I wanted to show you on these results is the following. So here, I'm showing you another way of estimating tidal heating in a way. It's the tidal temperature, which is just, the tidal flux divided by the Stefan-Boltzmann constant and 1/4, power 1/4. So it's very similar in shape, of course, of the tidal heat flux. But then you can compare it to other temperatures. So, and just before I compare to the other temperatures, so you can see that in a way, you can say with this plot that tides contribute to a few Kelvin for the temperature, the surface temperature of a planet, for instance, to potentially, more than a few hundred Kelvin. So if you compare it to the surface temperature that we use in our models, then you have this. This is the equilibrium temperature from Ducrot et al. 2020. In Ducrot et al. 2020, they also measured, I think it was with Spitzer, the brightness temperature for planets B and C. And also very recently, we also have the brightness temperature at 15 micron from James Webb. So, it's a same kind of conclusion as before. It's just another way of showing you that, potentially the tidal temperature, at least for planet B, could be, of the same order of magnitude or a bit less than the relevant temperatures for these planets. So meaning that tides might contribute a lot actually to the temperature of TRAPPIST-1b at least. And so then we can wonder, okay, but maybe we can try to observe it in a way. So as you know, as I said also in the beginning, TRAPPIST-1 has been intensively monitored with the James Webb Space Telescope. And in particular, some of the first observations that were done were a measure of the emission. So when the planet passes behind the star, so the secondary transits, and so you have a measure of the emission of the day side of the planet. And so we could imagine if for instance, planet B is very much heated by tide, it could the temperature of its day side could potentially be slightly hotter than it should because of the influence of tides. And also, there are some measures that are being done right now of phase curves for planet B and C in the TRAPPIST-1 system. And so with the phase curve, then you can have access also to the night side. So you could imagine, so you can see my Photoshop skills. So you could see here, potentially, you could potentially see some tidal heating emission on the night side of the TRAPPIST-1b planet or maybe C. And so with a phase curve between more day side and more night side, if you have a night side that is slightly hotter than it should, it might be then a signature of potential tidal heating. So just this works if the planet has no atmosphere. If your planet has an atmosphere, then things becomes more complicated. But if it has no atmosphere, maybe something like that could be possible. And then planet B and maybe C, but way harder, I guess, could be good targets. All right, so I see I'm running a bit late. So some take-home messages and some thoughts for maybe the discussion afterwards. So I showed you that the TRAPPIST-1 planets might not be exactly synchronous. So this is the work of Alexandre in preparation, hopefully submitted soon. We saw that TRAPPIST-1b and C could experience a very strong tidal heating. And for TRAPPIST-1e, it's moderate, but it could drive, volcanism, plate tectonics, and this could have an impact, for instance, on the composition of the atmosphere. And so some questions related to these 2 points. So what would be the impact of a non-synchronous rotation on the TRAPPIST-1 planets? So in terms of their climate, for instance, could we, I don't know, completely freeze over TRAPPIST-1e, or maybe, as I said, on the contrary, maybe increase the size of the ocean? It's something to be investigated. I think it could be interesting to look at that. Also, would the fact that the planets are not exactly synchronous, could this somehow impact the interpretation that we have of observations, for instance, with James Webb? I don't know, maybe. This is an open question. I'll be happy to hear what you think about that. And also, maybe a related question, could we infer the rotation from the observations? And for the tidal heating part, well, could we detect it, for instance, with the emission? So if tides are really, really active, maybe we can see it on the day side. Otherwise, with a phase curve, we might try to catch it on the night side of the planets. And also, I don't know if you realize, but the fluxes for TRAPPIST-1b and C were really, really high. And so probably it's going to melt part of the planets. So what would be the influence of melting part of the planets? This is also something of an open question. Probably it will reduce the tidal heat flux if you melt part of the planet, or maybe it's not that easy. So it's also an open question that I would like to address. So I will. This was the end of my talk. If I might, I will do a small advertisement because there will be linked to everything I've told you about in this talk. There will be 2 sessions at the EGU in Vienna in April 2024. So the first one is PS 5.3, and it's about the state of the art of modeling tidal interactions in rocky planets. So if you're interested by tides, I really encourage you to submit an abstract in this session. And the second session I wanted to advertise is one on TRAPPIST-1, actually, both observations and modeling. And so, yeah, likewise, if you have nice results about TRAPPIST-1 you want to share, please don't hesitate to submit something. All right, and now I'm really done. Thank you.
Thank you so much for the very nice talk, and I'll clap for everyone so that we have some sound.
I can see now. Stop the sharing. I can see.
There. Okay, thank you so much. That was very fascinating. I think you got a lot of thumbs up for the slides and the animations. I think everyone enjoyed it very much. Thank you. Yeah, I'm sure there are many questions. So who wants to go first? Maybe Claire wants to actually ask her questions in person rather than that I have to read them out from the text. Claire, would you want to do that? She's still there? I don't know. Ah, no. Okay, well, I guess I read out the question. So Claire had a question. Claire Wilmont from Cambridge, from Oxford, had a question about how the effect of the interior structure changes if you plot tidal heating as a volumetric heat flux instead of, I guess, per mass. And then, do the shallower mantles still result in much stronger heating, like you showed in your plot? It's in the in the text if you in the chat if you want to have a look at this.
Okay, so I will just share my screen again, but not put in a full screen so I can still see you. So I guess that she was referring to this plot, right? Probably.
Probably, yes.
Yeah. So what was the question? Because
so whether what if something would change if you would do it, but it's volumetric, right?
Yeah, this is volumetric, and this is like the integrated flux. So it's true that you can say, okay, here I have a much stronger tidal heat flux than here, but then here I have a bigger volume, let's say. But you can see that if you do the integration, you still have the strongest tidal heating for the bigger scores. So the difference in volume is not sufficient to counteract the difference in actual dissipation. So I don't know if that answers the question.
Yes. Oh, wait, I don't know if this is working.
Yeah,
Sure. Okay. Yeah, sorry, oh no, I'm getting bad feedback. But my question is just, I'm thinking of internal heating as something that happens volumetrically. So for example, if I'm putting this into like a parameterized model, I just want to have a tidal heating term in it. But then because these plots are all like a surface area flux from what I understand. So I just don't understand like why the lower volume mantles end up with less heating.
The lowest what? Sorry.
It wasn't this figure. It was the next one maybe. Yeah, like the biggest core. It has like the volume of the mantle is less. So I don't understand actually how tidal heating works. But can you just go back to basics to help me understand why these mantles have less heating?
Yeah. Okay. That was what I was saying. I guess that for the bigger mantles, in the end, you have less heat generated than for the smaller ones. So I don't know if I can explain it easily why, but okay, so there is a lot of steps that I didn't show here, and one major step, I guess, would have been to show you how, for instance, the Love number of the planets. I don't know if you're familiar with the Love number, but it's a measure basically on how the planet reacts to this perturbing potential that is the star here. And then this Love number, you can see how it changes with the viscosity and the shear modulus of the planets. And basically I don't remember exactly here. I should have put the plots to answer this kind of questions. But the viscosities change coming from the internal structure model allow at the frequency, the excitation frequency of this planet here, TRAPPIST-1c, you can see that the dissipation is going to be bigger for the blue case than for the purple one. So it's due to the values of mostly the viscosity and the shear modulus that give this behavior.
Okay, maybe we can refer the further discussion to once the paper is hopefully published.
Exactly, yeah. I will be happy.
Yeah. Maybe you can also chat in the Discord afterwards if you we want to get some other questions. Thank you both.
Thank you.
Yeah, Marek, please.
Thank you for a great talk. I had a question about the first part of your talk, actually, where you showed the evolution of the substellar point as a function of the time.
Yeah.
I thought it was really cool. And so I can see that this tidal evolution process is more of a stochastic change in the substellar point. But do you have any idea how this compares to non-integer spin orbit resonance states, and whether results for example, a 3-to-2 resonance are similar?
Yeah. So here the eccentricities are very small for the TRAPPIST-1 system. I don't remember the values exactly. But for these eccentricities, we do not expect the 3-to-2 resonance, for instance. The eccentricities are too low to have this resonance coming into effect. So basically, if you take the planets individually, they should be tidally locked. They should not be locked into another spin state. They should be tidally locked. And here, just what we show is the fact that you have, these planet-planet interactions are, enough to kind of desynchronize the rotation. But if you had another system with higher eccentricities, probably you could have, you know, maybe a similar thing with a 3-2 resonance that would not be exactly 3-2, but also, you know, like you would have some variation around the 3-2 resonance, for instance. We could imagine.
Thank you.
You're welcome.
Are there more questions? Yeah. I think maybe we do quickly. There's one in the chat. Is it expected? So Nicola Astudio de Roux asks, is it expected that the tidal heat flux is distributed homogeneously on the planetary surface?
Well, it's totally expected because our models are not 3D. But it's true that in a real life with a real 3D planets, you could you know, we see that in a solar system. There is a whole bunch of literature about the satellites of the one I'm speaking about is Saturn, but where you can have really differences of the tidal heat flux if you are towards the pole or towards the equator. But here, you know, our planets are just, you know, we just have a radial prescription for the, we are not treating any 3D effects. It would be much too complex, let's say, for planets that we know so little of. But I know that Tobias Meyer looked at that a bit. You know, okay, not tidal heat, but at least, you know, the solid convection in planets where you have a tidally locked planet. So you know, a side which should be, you know, way hotter than the other side. So some people are also looking at the 3D-ness or the 2D-ness of planets, but here no, we just have, you know, it's like it's homogeneous because we only took a 1D model basically. But it could happen that you have like a super volcano and most of the heat will go through the super volcano. So I don't know. I mean, I don't know. So yeah.
Barbara Suarez, please.
Hi, Emeline. Thank you for the amazing talk. It was quite interesting. I was curious about when you do the composition of the internal part of the planets. So more properly, what assumptions did you consider for the internal composition? Was it simply like iron for the core and silica for the mantle, or did you consider like a more herd-like approach? And in that case, the mantle will have like silicates like magnesium, olivine, pyroxene, and so on.
Okay, so what we did is like, okay, we started with the Earth-like composition. And so here the numbers that are given are for the composition of the core. And so basically we have 90% of iron, 2% of silicium, and a few percent of something more that add up to 100%. And so what we did for the planets with cores is that we fixed the sum of iron and silicium. So basically the sum of Fe and Si here should always be 92. So here, for instance, it's 92, etc. And then in that range, we were able to see, okay, the smallest core and the biggest core allowed in this framework. So the smallest core is easy because then you put everything in iron and you have 0 in silicium. But for the biggest core, we have you know, much less iron, obviously, and more silicium. So that's for the core, the planets with cores. And for the coreless case, you can see that here I'm talking about iron and magnesium. And so here, what we did is that it's the composition of a big mantle, let's say, and so we followed the paper of Elkin Stanton. I don't remember the year, I'm sorry, because all this work was done with, by Mariana. But basically here she tried to find the composition in terms of iron and magnesium that would allow to reproduce the mass and radius of the planet. And he made some assumption. I think it's whole perovskite. We do not account for a post-perovskite kind of rock or whatever. So these are the assumptions that we used.
And in those remaining 8%, did you account also for nickel, like the hard case scenario, or did you just like go for a very simple approach?
Yeah, so basically everything that is not iron and silicium, so nickel and the other things, are the Earth composition. We just change the iron and silicium content.
Okay, thank you.
Because otherwise, you have too many parameters to change.
Exactly. That's why I was wondering which ones were you changing and which one were you constraining, let's say.
So the ones that we change are these ones. Yeah.
Okay, thank you very much.
You're welcome.
All right, Tobias, Maya, please.
Hi, can you hear me?
Yeah.
Okay, good. All right, very nice talk. Thank you, and thanks for mentioning my work as well.
I didn't know you were here actually.
So I was wondering, for some of the models, I guess you produce enough tidal heating that parts of the metal could even be like molten, the upper parts or so. I don't know.
Yeah.
Is this something you think? Because I guess in that case you would generate less internal, less dissipation from like tidal heating, right? Is this something you think could be interesting to look at? Or?
Yeah, definitely. Yeah, so it's true that here we fix the structure, we compute the tidal heat flux, but yes, you have such crazy tidal heat flux sometimes that probably it will melt part of the planet. But it's something that we want to investigate, but we have not so far. And we want to try to couple our code that computes the dissipation with an internal structure code, and then which you can do the feedback of the tidal heating on the temperature profile, and then we compute everything consistently. So this is something that we would like to do at some point, but we are not there yet. So you'll have to wait.
Okay, awesome. Thank you.
Hey, since I don't see any questions anymore at this point, let's thank Emeline once more. Thank you very much for the very nice talk and very nice discussions afterwards. Can you quickly unshow your screen?
Oh, yeah, sorry. Yeah, I forgot that.
No problem. Yes, thank you. So thank you very much, Emeline. And just as a quick announcement before we finish today, we have not yet scheduled new talks for the new year, because in January we will have the in-person Rocky Worlds 3 conference in Zurich. There will be a few keynote talks that we hope to be able to stream, or at least upload the recording to the YouTube channel. And at some point in January, we will do an announcement about this closer to the day. And Emeline is, for example, also in the co-organizer of this meeting. And we will then announce the new talk series closer to the date, probably in January 2024. Thank you, everyone, and I wish you a good December and yeah, it's a good start to 2024. Thank you, everyone.
Bye. Thank you.
Thank you, everyone. Bye-bye.